The introduction of digital technology to architectural design has opened up new and exciting prospects for the development of architectural form. The free exploration of form has, of course, always been possible by the application of the humble pencil to paper, but the detailed specification of form by digital media allows architects to freely explore form in a controlled way. It also enables engineers to calculate the stresses that will occur within free-form structures so as to specify safe dimensions for elements. It makes builders aware of their exact shapes, which facilitates construction, and digitally controlled fabrication technology such as 3D printing can enable the economic realization of complex form. Patrick Schumacher of Zaha Hadid Architects has identified what he considers to be a new approach to form making based on the power of digital computing, in which architectural form is considered to be built up from tiny discrete elements which at the macro scale give buildings the character of continuous flowing surfaces rather than of assemblies of larger elements. He has termed this process a topological approach to design, and previous methodologies, based on assemblies of larger elements such as beams and columns, as being typological. Schumacher argues that a new design freedom has been facilitated by exploiting the power of digital computing, and that this enables shapes to be manipulated and controlled by sophisticated software. He describes this as a new engineering intelligence made possible by the digital revolution and refers to this new architectural style as parametricism, architecture that can harness the structural efficiency of an interconnected network, an era of structural fluidity and structural optimization in which digital technology retools the engineer and allows the structural forces to flow freely through the surfaces provided by the architect. Schumacher's statements are misleading, however, because although it is true that the architect may be free to invent new and interesting forms which digital technology allows engineers to analyze and builders to fabricate, the methodology is not in fact capable of directing the resulting internal forces, as Schumacher suggests. Only the basic physics of the situation, the effect of gravity on mass, can do that. So it is not correct to assume that these freely imagined forms can harness the structural efficiency of interconnected networks, or that they can be made efficient by clever digital manipulation. In another new development, Neri Oxman and the Mediated Matter Research Group at the MIT Media Lab are considering afresh the ways in which efficient and non-wasteful forms have evolved in natural organisms, and are exploring how these might be allied to advanced techniques of design and fabrication to create a new kind of architecture. This has been part of a more general revival of interest in biomimicry as a source of architectural ideas, as summarized, for example, in Michael Pollan's book, Biomimicry in Architecture. The biomimicry approach is often promoted through statements such as Julian Vincent's, "In nature, materials are expensive and shape is cheap," an engaging aphorism that implies that nature always uses material efficiency. This statement is, however, highly simplistic in its description of what actually occurs in natural organisms. The latter grow by cell division, rather than by being fabricated artificially, into shapes that have evolved through natural selection to accommodate complex and very specific multiple functionalities, which on the one hand are very different from those which humans require of buildings, and on the other are not necessarily of the highest efficiency, because other properties may be more significant. It is important to bear in mind that nature may be characterized, depending on specific circumstances, by great parsimony or by great profligacy. The forms produced in nature are related to the performance of creatures as organisms in relation to their environment, and may not actually be relevant to an application in humans' building projects. Their visual excitement, which may be what principally interests architects, is a matter of culturally determined perception. The imitation of the purely visual qualities of natural forms, without a proper understanding of why these forms have originated and of their multiple functions, is an unreliable procedure for the creation of buildings with the types of physical properties required for sustainable architecture. The opportunities offered by digital technology for the development of new types of architectural form are very exciting. But there are nevertheless certain realities that intrude into any attempt to make a physical object, such as a building, that have to be recognized by designers who wish to act responsibly, as opposed to dreamers and fantasists. Recognition of these realities will be especially relevant to design in a world in which the mitigation of climate change is emerging as the highest priority. Let me illustrate this with a story that begins with a question. And the question is, these laws of Newton, are there no exceptions? This was a rhetorical question that was asked of a physicist expert witness by a frustrated defense lawyer in court proceedings that followed a vehicle accident. The expert witness had demonstrated that by considering the mass of the vehicles and their final locations following the accident, it could be demonstrated, using Newton's laws, that the individuals involved had been driving at excessive speed. Repeated questioning by the lawyer had failed to reveal any inconsistencies in the expert witness's testimony, hence the lawyer's annoyance. The exchange between the lawyer and the physicist highlighted an essential difference between human-made law and the principles that govern the behavior of physical systems, which is that the performance of the latter is determined by agencies that are fundamental and unalterable. Our human understanding of these laws and their complexity continues to deepen as science advances, but the laws themselves are part of the workings of the universe that we inhabit, and are not affected by human desires or constructs. That there are no exceptions to the laws that govern physical behavior is an axiom that has great relevance in the field of architectural design, which, throughout the modern period, has been informed by many ideas and theories that are largely unconnected to physical reality. From aphorisms such as "Ornament is crime," Adolf Loos, "Glass destroys hatred," Bruno Taut, "Less is more," Mies van der Rohe, "Less is a bore," Robert Venturi, to the sophisticated French philosophy-based constructs of much of the architectural theory of the late 20th century, the ideas that have informed new architecture in the modern period have been largely matters of opinion, unrelated to physical realities. They are not statements of fact, and they have resulted in buildings that have poor physical properties, that make wasteful and extravagant use of materials, and that perform poorly in respect to all aspects of function. Such theories make unreliable guides for designers wishing to produce buildings that have particular physical properties, such as a low carbon footprint, because the latter is determined by the laws of physics rather than by polemically expressed views. There is a danger that the present excitement with the possibilities offered by digital applications in design may cause architects to repeat the environmental mistakes of the modern era. If architectural design is to contribute to the mitigation of the climate emergency, such mistakes must be avoided. A building's structure accounts for between 40% and 90% of its fabric. Structural design for low consumption of material, and therefore for low embodied carbon, is closely related to form, because the internal forces that loads generate within structures and that determine the amount of material that they must contain are almost entirely dependent on all aspects of their shapes, both their overall forms and the detailed geometries of their constituent elements. The act of designing a building, that is of determining its form, is therefore also an act of structural design that will have a significant effect on its carbon footprint. In the quest for structural efficiency, the form-searching techniques of the pre-digital age that found expression in buildings such as Gaudi's Sagrada Familia in Barcelona, or Frei Otto and Ted Happel's timber lattice shell at the Mannheim Multihalle, were based on physical models that enabled the effects of gravity on mass to act directly. Computer-based form-generating software that is programmed to search for efficient forms produce similar results. In the physical laws that govern these exercises, there are no exceptions. And as I've already emphasized, the form generated is not a free choice. There is therefore a danger that the new approaches to design being promoted at the beginning of the 21st century by opinion formers such as Oxman and Schumacher, be they biometric, parametric or topological, will simply perpetuate the design methodologies generated by the polemical statements of previous modern architectures, and produce forms that are equally inappropriate for buildings in an age of climate emergency, because they are not related to the physical realities and functional requirements of buildings. So what are the essential truths based on the laws of physics that have to be accepted if an efficient, low-carbon architecture is to be produced? The first of these is a realization that some things cannot be changed by new design methodologies or methods of manufacture because they are fundamental, determined by the basic physics of the world. A second is that to achieve high technical performance, form must be matched to physical function and physical reality, not to polemically expressed theory, and not even necessarily to programmatic function, which is what Louis Sullivan was referring to in his famous aphorism, "Form shall ever follow function." The efficiency of a structure, as measured by the amount of material required to give it adequate strength, is predominantly determined by the types of internal force that loads generate within it. The most important distinction is between loads that cause elements to bend, transverse loads, and those that produce internal forces that are axial. As is discussed in my book Structure and Architecture, which, by the way, is a very good read. This is a crucial difference because axial forces can be resisted with elements that are an order of magnitude smaller than those that are required to resist bending. And the type of internal force that occurs is entirely dependent on the overall form of the structure in relation to the pattern of load that it carries. The range of efficiencies that can occur is very large, as may be demonstrated by the following examples of very well-known buildings. In Le Corbusier's Villa Savoye, a beam depth of around 300 mm was required for a span of approximately 5 meters. At the Sydney Opera House, a shell frame thickness of around 2 meters was required to achieve a span of 70 meters. The CNIT shell in Paris spans 200 meters with a total shell thickness of only 120 millimeters. Using the admittedly rather crude device of the ratio of span to thickness as the measure of the efficiency of these structures, the differences are remarkable. The least efficient is the Villa Savoye with a ratio of 13. Next comes the Sydney Opera House at 35. That of the CNIT shell is 1,666. The differences in efficiency between the first two structures are significant, with the Sydney Opera House being 3 times as efficient as the Villa Savoye. The CNIT shell is 2 orders of magnitude, 100 times more efficient than the other two. The differences in efficiency are almost entirely due to form. The very high efficiency of the CNIT shell is the result of the combination of an overall form which is a parabolic curve and the geometric configuration of its cross-section. I've heard people describe the CNIT shell as having a natural form. This is not accurate. It is a form that responds to the laws of physics, which nature obviously must also do. The parabolic form generates internal forces which are pure axial compression. The shape of the shell's cross-section is a hollow box, consisting of two 60mm thick skins forming the outer surfaces, separated by 60mm thick diaphragms to give an overall depth of 1.5 meters. This is a highly efficient shape of cross-section for the resistance of compression, where the possibility of buckling, a bending phenomenon, has to be allowed for. The slight corrugation of the shell surfaces provides efficient resistance to any tendency for local bending or buckling to occur. The inefficiency of the other two structures described here is also due to a combination of their overall forms and the cross-sections of their elements. The very low efficiency of the Villa Savoie's structure is due to an overall form that produces only bending in the horizontal elements. The better performance of the Sydney Opera House shell is due principally to its overall form producing internal forces that are combinations of bending and axial force, which reduces the amount of bending that is present. Both of these structures have elements with solid cross-sections, which is an inefficient configuration for the resistance of the bending type of internal force that dominates their responses to load. Comparison of these three structures demonstrates the essential features of the effect of form on structural efficiency. The key question is the amount of bending that is produced, and this is dependent on the overall form. The shapes of the individual elements at a detailed level, cross-section and longitudinal profile, are also crucial. The important issue is again the efficient resistance of such bending as may be present. Cross-sections that resist bending efficiently have the material dispersed from their centres, hollow tubes, eye sections, and so far as longitudinal profile is concerned, features such as triangulated geometries. The comparison of the three structures demonstrates that if the shape of a building is freely determined and not related to the basic physics of the situation, the resulting structure is likely to be inefficient in the use of material, and that the degree of wastefulness will probably be very large. There are no exceptions to this rule. If structural mass is to be minimized, the form adopted is not a free choice. The use of digital technology to experiment freely with form, as proposed by designers such as Schumacher and Oxman, risks repetition of the wasteful practices of the modern era, if not tempered by recognition of the physical realities of the relationship between form and physical performance. The large quantities of steel that were required to realize the Heydar Aliyev Center in Baku, a building that relied heavily on digital processes, provide a further recent example of what occurs when the laws of physics are disregarded in the exercising of a free choice of form. The overall form generates high levels of bending that require the use of a steel space frame structure of very high carbon footprint for its realization. Spans were variable because the roof canopy is supported intermittently on an underlying reinforced concrete armature, with maximum spans of around 30 meters, which gives an average total tube section thickness of around 60 millimeters, gives the structure a span to thickness ratio of 500, which makes its efficiency a third that of the CNIT shell. It is, however, made from steel, a material that is around 7 times stronger than reinforced concrete. If it had been made in reinforced concrete, as the CNIT shell was, the equivalent thickness would have been 420 millimeters, and the ratio would be more like 71, which would put it in the same efficiency category as the Sydney Opera House. In view of the variety of structural components involved, the structure is also typological rather than topological, and involved high inputs of energy for design, manufacture, and construction that overall contributed to a very high level of total embodied energy. Another essential reality that must be addressed before any proposal for a low-carbon structure can be taken seriously is the effort required to build it, which is obviously affected by the level of complexity of its form. It is an unfortunate fact, yet another intrusion of inconvenient reality, that the forms that minimize the amount of material required for a structure are complex and therefore difficult to make. Space frameworks are more efficient than solid slabs. Eye-shaped cross-sections are more efficient than solid rectangles. Tapered profiles are usually more efficient than parallel sides, and curvilinear forms more efficient than rectilinear ones. State-of-the-art methods of fabrication, such as 3D printing, can mitigate the difficulties of making complex forms to some extent, but do not eliminate them, and the machines and processes involved produce high carbon footprints. This is yet another reality that will have to be taken seriously by designers of buildings. In future, it will be the total carbon footprint of buildings that matters, and this will not necessarily be minimized by adopting efficient forms that reduce material consumption, or the flowing forms derived parametrically. The energy involved in design, fabrication, construction, and subsequent maintenance will be important additional considerations. All design involves compromise, and in structural design, a balance has to be struck between the complexity that will minimize material consumption and the simplicity that will reduce the resources required to design, build, and maintain a structure. For responsible design in a low-carbon economy, the goal must be overall economy of means, rather than the minimization of any particular input. In the context of the horizontally spanning structures required for architecture, the most significant factor that influences the best compromise that will deliver overall economy of means is span. The longer the span, the greater is the level of complexity that is justified in the pursuit of overall economy of means. The parabolic form of the CNIT shell was fully justified for a span of 200 meters. For buildings of more modest scale, a much simpler structure normally provides the best compromise and lowest carbon footprint, even if it is less efficient in its use of material. The inefficient structure of the Villa Savoye was entirely appropriate for the spans involved, due to its simplicity. In contrast, the organically based or free-flowing forms, shown here, are mostly inappropriate. Their engaging forms are overly complex for their scale and not related to their physical function. If low overall carbon footprint is to become the high priority in architecture or any other branch of design, the achievement of economy of means with structure, normally the largest contributor to embodied carbon, will have to be given greater importance in the design agenda. The realities outlined above will then have to be taken seriously, and in the case of buildings, this will place considerable restrictions on the choices of form that are available to architects. The implications of form in all its aspects and the question of buildability with available technologies, albeit the most advanced, will be essential considerations in relation to design for low carbon. Architects will have to understand the true implications of any form that they propose, and these will have to be based on an understanding of the physical realities of the situation to which there are no exceptions, rather than culturally derived theory. As a philosophy of design, the idea of achieving overall economy of means is not new, and was well described by two prominent engineers of the mid-20th century, Pierluigi Nervi and Eduardo Torroja, who also demonstrated its application in their respective practices. It involved the development of a design from knowledge of the relationship between form and structural performance, of the properties of materials, and of available construction techniques, all purely technical matters. We see examples of a similar approach being adopted in the present day by Shigeru Ban. And note that where a short span is required, a simple structural form is used, as on the left here. Central to the thinking of Nervi, Toroja, and Ban was the idea that the designers of infrastructure should be under a moral obligation not to waste society's resources, or the planet's, one might now add. The adoption of such an ethical position was generally lacking in the modern period, in which architects were often congratulated for excess rather than for economy. It has assumed much greater importance in the present day of climate emergency. The greatest challenge that architecture must now face is to amalgamate design methodologies that recognize unalterable physical realities with the cultural aspirations that elevate architecture from an exercise in mere building to that of an art form. A reconsideration of what is regarded as beautiful or interesting visually and spatially may be required. And this may be just one aspect of a much greater adjustment of the mind that will have to occur if buildings that are environmentally sustainable are to be produced. In future, architects will certainly have to work with nature rather than against it, but not through the simplistic imitation of natural forms, as in much of biomimicry, or in the freely determined forms of parametricism, and certainly not with the idea of exercising domination over the natural world, as in much of the spirit of modernism. In future, architecture will have to be seen as part of its wider environment. The rules to which there are no exceptions will have to be understood and respected with humility. As Sullivan suggested, nature is our friend, not our implacable enemy. It is my belief that it is of the very essence of every problem that it contains and suggests its own solution. This I believe to be a natural law. What Sullivan was suggesting is that we should look to the essence of the problem to find our solutions, and not to externally imposed, culturally derived theory. It is an idea that has great relevance in the present day. Its implementation will require a fundamental change in the culture of architecture.